残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ。
Hey Anna, is doing math cool?
Oh my god, stop asking me that.
Okay guys, we're back with section 4.9, Antiderivatives. It's about to get real. This is where the rubber meets the road. This is where we're going to start to see the whole picture of what's going on in this class. The idea is that when we started talking about differentiation, our goal was to find the derivative of a function f. We found f prime given f. The reverse process, which, if we're going to call it anything, we might as well just call it anti-differentiation or something like that, undoing a derivative, this is equally important. Given a function f, we're going to look for an antiderivative. That is, another function, let's call it capital F, whose derivative is f. That is, a function big F such that big F prime is little f. Basically, we've been taking functions f on over to their derivatives using a derivative in here. Now we're going to figure out how to go the opposite way. What is this operation? We can take a function and send it to a derivative. But what is the thing that sends a derivative back to a function? Alright, we're going to learn all about this, and it turns out that the answer is really cool. This is the other half of calculus. This is the other part of what's going on. And as it turns out, while derivatives, you might not feel like they're easy, but all things considered, they're relatively doable, at least. It's possible to do derivatives. I don't know if I want to say that they're easy, but compared to the reverse process, they're easy. So the reverse process, weirdly more interesting. All right, let's get into it. But we need a definition to really motivate what's going on here. Basically, exactly what I just said, definition 7, an antiderivative. We'll say that a function, capital F, is an antiderivative of little f on an interval I if big F prime is little f for all x in I. So it's totally possible to have an antiderivative only on a certain interval. Maybe, you've got a function that looks, here's a line with slope 1, say. Okay, go down using a derivative. I'm going to just kind of separate these off. Going down using a derivative, you get something over here. This isn't an xy plane. Here, let me make that a little bit clearer. So what I'm trying to draw here, I'll actually draw it. Here we go. Here's the gist. All right, cool. So maybe you've got a function and it looks like a nice line. Yeah? Then the derivative is just flat, right? The derivative of this function would just be flat and it would have a value of the slope of that line. Okay, it's totally possible to have only a derivative on a certain interval. So for example, maybe you can see that if I just started to change things up past here, it becomes a wiggly function. Okay, then on this interval, this guy up top is an antiderivative of this guy down low, but only on this interval I, on this little chunk. Over here, no, not working at all. But on these intervals, this guy is an antiderivative of the bottom guy. Okay, so it's totally possible to have an antiderivative only on an interval, not on the whole thing. Any derivation is a local concept the same way derivation is. Derivatives are telling you about the slope of tangent lines. It's totally possible to only have a tangent line at some points. Think about functions like absolute values, stuff with a sharp point. It's got derivatives everywhere except at that sharp point. So it is possible for derivation to fail locally. Similarly, it's possible for antiderivation to fail locally in the same ways. None of this is particularly important in terms of what you need to think about. The only thing you need to focus on is that antiderivatives are undoing a derivative. They're things that give you a desired derivative, a function whose derivative is something that you've already specified. Basically, you give me a derivative. If I'm finding an antiderivative, my job is to give you a function that derives to that thing. Okay, cool. Let's check out some of the nuances involved with antidifferentiation. So the first nuance of antidifferentiation is that antiderivatives are never unique unless we specify additional information. But just generally speaking, antiderivatives are never unique. You get a family of antiderivatives. The idea of it is just that since a derivative can be split up over a sum, then if big F is an antiderivative of little f, that is, if big F prime is little f, then the derivative of big F plus c for any constant c, any number, f plus 5, f plus 2, f minus 137, take a derivative, you still get the same thing. That is, f of x plus c, for any constant c, take a derivative. This is f prime of x plus c prime, and if c is a constant, this is just f prime of x plus 0. And if f prime of x is little f, then this is still little f. So for every real number c, you get another antiderivative. This is, if you want to say, a family of antiderivatives. So if we have f, big F, any antiderivative of a function little f on an interval I, then all of the antiderivatives of little f on I have the form big F plus c, where c is any old constant you want. Basically think of it like this. If the derivative is picking up the slope of a tangent line, then vertical translations of a function don't do anything in terms of changing a tangent line. Let me draw a graph. It changes the tangent line, but not its slope. The derivative gives you the slope of the tangent line, so everything's all good at the end of the day. So say you have, oops, still doing a line there. All right, say you have this little parabola, yeah? Pick a point on it. Here, we could grab a tangent line through that point. Okay, now if I move this function just a little bit down, then if I go back and I grab a tangent line at the same point, notice, if I've drawn this well, then I should have the same slope. That is, these two guys same slope. So basically, it's like this function, this blue one here, and this one here, they're just parallel translates. They're vertical translates. And they have the same tangent lines, at least up to the exact same translation. I've moved this point from here down to here. I've moved this point from here down to here. I've moved every single point just vertically down. Nothing has changed in terms of rates of change. All that's changed is height, you know? Basically think of it like you know, the steepness of a ramp should be the same whether you're at sea level or in Wyoming, way above sea level. Same thing, right? Take a inclined plane and put it at sea level, then take it in an airplane. Has the slope of the inclined plane changed? No, it's just higher up. That's all that's going on. So basically, it's like take a function f, you get out a whole family of antiderivatives, and they're parameterized by the real numbers. Basically, it's like f goes to, you know, big F plus C, where C is sliding along this number line. It can be any value wherever the heck you want. Think of it like a slider. You're just moving a function up and down, just like this. Tangent lines, they might change in terms of where they are. Their slope doesn't change. The derivative doesn't pick up vertical translates, parallel translates along the y-axis like that. So ultimately, you don't recognize this in terms of antiderivatives. The derivative doesn't pick it up, neither does the antiderivative. You get an infinite family of antiderivatives. This all just comes from the fact that the derivative of a constant is 0. Because of this, we get an infinite family of antiderivatives for every function which even has an antiderivative. We'll talk more about which functions have antiderivatives in a bit, but for now, this is a pretty good first step in understanding what's going on. A function gives rise to an infinite family of antiderivatives, and there are exactly as many. This is the important word right here, all of the antiderivatives of a function f. There are exactly as many antiderivatives of a function f as there are real numbers. There's one for every single real number c. And that's it. There's no more. It's one antiderivative for a given function for every single number. All right, cool. In practice, all this means is that we just generally write f plus c to symbolize it's this function up to a parallel translate. That's the antiderivative. And what we mean by this is that this is the family of antiderivatives, the set of functions parameterized by the real numbers that all have the same slopes of their tangent lines, just maybe with their tangent lines shifted up or down. Okay, cool. Let's see if we can do something with this. So overall and generally speaking, finding antiderivatives is harder than finding derivatives. But this is just a general rule. There's not as organized a method to get there in general. But for many functions, it is essentially the exact same process. Just go in the opposite direction of every single result we have from the first part of class. So for example, let's find an antiderivative of the function little f of x is 3x squared. Alright, we're looking for a function whose derivative is 3x squared. If you've been paying any attention in this class at any point, it shouldn't be hard to do this. We all know that the derivative of x to the third is 3x squared. That's just the power rule. That's super straightforward. So, an antiderivative of little f is 3x squared. One antiderivative is x to the third. And in fact, using that previous theorem, theorem 17, the complete family of antiderivatives are all of the functions capital F of x equals x to the third plus a constant. So C, any constant you want. Arbitrary means pick any dang one you feel like. It works for every single one. F of x plus C, this family of functions, this slight abuse of notation, maybe, here is just a way of saying all of them at once. It's not really an abuse of notation. Plug any actual constant C in there, and this is just a function. But when we're leaving this as the ambiguous C, what we're trying to represent is an entire set of functions. X to the third plus 1, x to the third plus 2, x to the third plus 3.178. Who cares? Any number. This is a whole family of functions because all of these guys, this is the whole family of antiderivatives because all of these guys derive to little f of x. All of these guys, no matter which number c you choose, all have a derivative of 3x squared because the constant derivative kills it. It doesn't pay any attention to it. It just throws it away. Cool. All right. So it seems like this is tractable, but gosh, we need some notation. If I have to write an antiderivative is every single time, oh my gosh, I'm going to get a little bit annoyed. So let's go to the notation and let's talk about how we write this idea down in a formal mathematical way, or at least the way that's customary. Cool. Okay, so the notation we'll use here is a little bit unfamiliar. So when we wrote d dx of f of x, that meant take the derivative of f of x with respect to x. We need an analogous notation for derivatives. We need an analog of this to handle antidifferentiation. So for historical reasons, which we'll talk about a lot in the next section, the notation that means find the antiderivative of f is the so-called indefinite integral, which is just this weird looking S shape followed by f of x, followed by, and this is always important, a little dx guy. Okay, this thing right here, this bad boy, is what we'll use to say find the antiderivative. And it's important to have all of these components. Every time you get one of these integral signs, these big drawn out S's, which is exactly what they are. They're just a stretched out S. There is no fancy secret behind it. It's a stretched out S. That's it. Every time you see one of these, it needs to be followed by a function, which we'll call the integrand. So an integral is followed by the integrand. The integrand is the thing that we're going to integrate. Okay, and then we close it off. Think of it almost like a closed parenthesis with the differential, just dx. Now this has a meaning, and there's a variety of different ways to view it. But in terms of what you need to know for this class, dx simply means that x is the independent variable, or it's the variable that we're integrating with respect to. You know, the same way that d dx means that the variable we're deriving with respect to is x. Same thing's going on here. This dx is just saying, hey, we're using x as our variable with respect to integration. So the notation integral sign f of x dx, read as the indefinite integral of f of x dx, this represents all of the antiderivatives of f. When the integrand is a function of a variable different from f, say g of t, then we would use dt instead of dx for this. So we'd write integral sign g of t dt instead of dx. to represent the antiderivatives of g. For example, in the context of that previous example we just did, example 26, we found that the indefinite integral of 3x squared dx was x to the third plus c. All right, cool. It's a little bit weird notation at first. You'll get used to it. It's actually pretty simple and pretty intuitive once we talk about more of the justification for why we write things this way. All you really need to keep track of is that this thing, this integral sign, is a big S. It's a stretched out S. Instead of writing an S like this, I've really stretched it out. So it's like that. That's all an integral sign is, a big old S. Then you put the function, and then you put d whatever the variable is. This is every component of what we're writing here. Big S, function, whatever the variable is, d whatever the variable. And then on the other side, just write your answer, which should always include that plus c. It's a function that derives to this guy, and then you throw a plus c on there, so you have all of them. Okay, cool. Let's do some more. Okay, so for the time being and for the foreseeable future, or at least for the immediate future, what we're going to do is basically just take all of the results from the first part of class, we're going to reverse them. That is, instead of saying the derivative of this function is this thing, we're going to say the integral of this thing is that function. So let's start it off with the power rule, just to get used to what we're saying. So for p not equal to -1, the indefinite integral of x to the p dx, the family of functions that whose derivative is x to the p, is just 1 over p plus 1 times x to the p plus 1 plus c. So think of it like this. If I had told you this statement, you would have been like, well, duh. If I had said, hey, ddx of 1 over p plus 1, x to the p plus 1 plus a constant is equal to, well, x to the p, you'd have been like, obviously. Here's literally everything that we're doing when we're turning this into an integral result. Here's everything that's going on. And notice this p not equal to -1 is just so we don't have a 0 in the denominator right there, and just so this actually is something other than 0 in that power. But, you know, any situation where you have something other than x to the 0, which will always be 1 except at 0, in which case it's not even defined. So, if we're dealing with something that makes sense in terms of the power rule, there we go. Here's a derivative law that we already know. Here's everything we do to turn this into an integral. All we do is get rid of the dx, scribble out those parentheses, put an integral and a dx. Wow, we did it. It's this thing that's right here, and then the other side is right there. Oh wow, so complicated. I know it looks kind of messy on the page there, but literally all we did, the entirety of what we just did, is take a thing we know about derivatives, and we erase the derivative, and then we put an integral and a dx on the other side. That's it. Now, you have to be a little careful to make sure you phrase things in the right way where you can just do this trick. Basically, what I'm trying to get at right there is that if I hadn't put this this plus c in, then I could not just do this. I'd have to make sure that I have a plus c to do this little trick. You know, if I don't have that plus c, then I'm not really done. I always have to have that plus c when I'm writing an indefinite integral, just because otherwise I've missed some solutions. Without that plus c, I'm missing every parallel translate of the function. So, all right, let's try out some more examples of converting derivative results into integral results. So let's try out the constant multiple rule. You know that d dx of a constant k times f of x is just k times d dx of f of x. That is, you can always pull a constant out of a derivative. All right, so if we're turning this into an integral, basically all we're going to do is go, hey, integral of k times f of x, always remembering to write that dx, is the same as k times the integral of f of x dx. Same thing as before, we're just taking a derivative result and we're turning it into an integral result. So there we go, the constant multiple rule. I can pull out a constant multiple from an indefinite integral, just for exactly the same reasons that I can pull a constant multiple out of a derivative. Huh, cool, easy. Similarly, we have the sum rule. We can take the integral of a sum, we can turn it into the sum of integrals. So the indefinite integral of f of x plus g of x dx is the indefinite integral of f of x dx plus the indefinite integral of g of x dx. All right, so as you would hopefully expect, indefinite integrals work somewhat similarly to derivatives. Since indefinite integrals are just undoing a derivative, I would hope that the properties would apply, right? So yeah, cool. Works out reasonably well. Let's try an example. Okay, on to an example. Example 28. Let's determine the indefinite integral of 3x to the fifth plus 2 minus 5 times the square root of x dx. Okay, so first thing I'm going to do, I'm going to start by making this a little bit more manageable. I'm going to break this down into bite-sized chunks using the sum and difference property of indefinite integrals. That is, I'll break this into 3 smaller integrals. I'll turn it into the indefinite integral of 3 times x to the fifth dx plus the indefinite integral of 2 dx minus the indefinite integral of 5 times the square root of x dx. Now, I'll try out the constant multiple rule. That is, I'll take out all of these constant multiples and make my life a bit easier. So I'll get 3 times the integral of x to the fifth dx plus, and this part maybe is less obvious right away, the integral of 2 dx, let's just turn that into 2 times the integral of 1 dx. Okay, minus 5 times the integral of the square root of x dx. And just to save myself a step, I'm going to write this as x to the 1/2 dx. Just because the square root of x is x to the 1/2, and I'm going to find it easier to have this exponent there instead of writing it as a square root. This is pretty much identical to why we would do this in using the power rule when we first started taking derivatives. All right, cool. So now we can use the power rule for integrals. So what derives to x to the fifth? Maybe 1/6 x to the sixth. That is, using the fact that, and I'll just write it down over here, the integral of x to the p dx is 1 over p plus 1 x to the p plus 1 plus c. What I'll get here is, and I'll write it like this, 1 over 6 x to the 6 plus c. Nice. Okay, cool. So I'm going to maybe even write c1 right here because I'll get 1, 2, 3 constants, one from each of these integrals. This is ultimately something we don't need to worry about, but let's do it for the moment and then talk about why at the end. So, next integral. 2 times the indefinite integral of 1 dx. You might think to yourself, I don't know how to do this. But 1, is that the same as x to the 0? Yeah, it is. Dang right. So this is 2 times 1 over 0 plus 1. So 1 times x to the 0 plus 1. That's just x. And of course, plus c. This time I'll write c2 to distinguish it from that previous constant c1. Finally, the last one. And this one is maybe slightly trickier if you're not careful. So we'll get minus 5 times, now the indefinite integral of x to the 1/2 dx. I'm still just going to apply this power rule. So it's going to be 1 over 1/2 plus 1. So I'll write this time. X to the 1/2 plus 1 plus c. And this time I'll call that c3, just to distinguish it from the other c's we have flying around. Cool. Okay, so let's put it all together. 3 times 1/6, that's just 1/2, right? 1/2 x to the 6 plus 3c1 plus 2x plus 2c2 minus 5 times, well, let's see, let's reduce this right here. So 5 times 1 over 1/2 plus 1. 1/2 plus 1 is 3/2, right? 3/2 on the bottom of a fraction is 2/3. That makes sense. Okay, so 5 times 2/3 is 10/3. And if we got that minus sitting around, this will just turn into minus 10/3 x to the 1/2 plus 1. That is just 3 over 2. And then minus 5 times c3. So I have a lot of c's flying around here. This seems inconvenient. So I got 3c1, 2c2, minus 5c3. If they can be whatever they want, then 3 things that can be whatever you want, you can get exactly the same place as if you just have 1 thing that can be whatever you want, right? So I might as well combine all of these guys. Put all of these guys together into a single thing, a new thing. Put all of these guys into a single thing. So let's basically let c equal 3c1 plus 2c2 minus 5c3. Just let c without any subscripts be that. Then we can get our final answer. So I should switch back to the other color, keep it consistent. I'll get 1/2 x to the 6 plus 2x minus 10/3 x to the 3 over 2 plus c. Hey, that is what I am thinking is a pretty nice final answer. Very cool. All right, good to go. So notice something. If I hadn't put all of these c's in all the way through, if I had instead just gotten rid of all of these c's and just thrown a plus c at the end of everything, I would have ended up in exactly the same place. And I wouldn't have had to have all this mess flying around, right? So this is really a convenient thing. Basically, here's the easy memory device. Once the integral goes away, the c is here to stay. Once you get rid of those integral signs, once you get rid of even a single one, put a plus c at the end of every line after that. You don't have to ever put more than one. Just as soon as an integral sign goes away, every line of work after that should have a plus c. If you do this, you'll always be right. And you don't have to keep track of C1s and C2s and C3s or any of that nonsense. Just put a C after every single line once integral signs disappear, and you'll always be good to go. But hey, cool. And even better, here's one last thing to end this problem with. Integrals are very nice, or at least indefinite integrals are very nice, because they come built in with a way for you to know whether or not you got the answer right. You can check your work with almost no effort, because all you have to do to know that this guy down here is the right answer is take a derivative. So, d dx of 1/2 times x to the 6 plus 2x minus 10 over 3 x to the, oops, that's a weird 3, x to the 3/2 plus c. This, and this is just some scratch work. This isn't part of your answer. This is just a way that you can check your work. This guy, just run through a derivative real quick, and you can see that you got it right. Let's do it. So the derivative of 1/2 x to the 6 is just 3x squared plus the derivative of 2x, that's just 2, minus 10 over 3 times x to the 3 over 2. Take the derivative of that, and I will get 10 over 3 times 3 over 2. So minus 10 over 2, that's just minus 5. X to the 3/2 minus 1, that's 1/2. And that c just goes away. Hey, wouldn't you know it? Other than writing that x to the 1/2 as a square root, I have recovered the thing that I started with inside my integral. I have recovered my integrand. These guys are the same. That's how I know I did it right. If you get an answer and you take a derivative and you don't get the integrand, you made a mistake. This is what an indefinite integral is defined to be. It is the family of functions that derive to your integrand. So, all you have to do to check your work is take a derivative. Pretty cool. Let's do another example. Okay, on to another example. Example 29. Here I'm not going to write everything out in full detail myself. I'll save us some time. I've got a little bit of it typed. So example 29. Let's determine the indefinite integral of, whoa, the quantity 4x to the 19th minus 5x to the negative 8th over x squared dx. This does not look like something we're ready to handle, but it turns out we are. So the idea here is that I can take 4x to the 19th minus 5x to the negative 8th over x squared, and I can convert it into something a little bit easier to deal with. So think of it like this. 4x to the 19th minus 5x to the negative 8th over x squared. I can turn this into 4x to the 19th over x squared minus 5x to the negative 8th all over x squared. Cool. And then, using the fact that I can reduce these bad boys into respectively 4x to the 17th and minus 5x to the negative 10th, now I'm in a situation where I can use the power rule. Okay, cool. So there's a little bit of pre-processing I have to do. I have to make sure that I'm in a situation where I can use the power rule well. But I can just do a little tiny bit of algebra and I'm ready to go. So this guy, I've already put it right in here. All I got to do now, break up the integral, break up this indefinite integral into two pieces. So the indefinite integral of 4x to the 17th minus 5x to the negative 10th dx turns into the integral of 4x to the 17th dx minus the indefinite integral of 5x to the negative 10th dx. Now I'll apply the constant multiple rule. So this is the sum/difference rule. And now I'll do the constant multiple rule. Okay. So sum and difference and constant multiple. I did the sum and difference right here, and now I'm going to pull out the constant. So indefinite integral of 4x to the 17th dx becomes 4 times the indefinite integral of x to the 17th dx. And the indefinite integral of 5x to the negative 10th dx becomes 5 times the indefinite integral of x to the negative 10th dx. So I just broke this down into bite-sized pieces. And now that I have 2 powers of x as integrands, and I can deal with those guys using the power rule. The backwards version of the power rule for derivatives. That's all it is. So indefinite integral of x to the 17th dx is 1 over 17 plus 1. So 1 over 18, x to the 17 plus 1, x to the 18th. Okay, 4 times 1/18th, x to the 18th, minus 5 times, well, the indefinite integral of x to the negative 10th dx, and you got to be a little careful here, is 1 over negative 10 plus 1. So that's minus 1/9. X to the negative 10 plus 1. So that's x to the minus 9. And like I said before, we don't have to bother with different constants for every single indefinite integral we do. Once the integral signs went away, the plus c is here to stay. I put that at the end of it, and it's not going anywhere. It's going to stick around there. I don't even have to think about it other than just rewriting it every time I do a new line. But luckily, we only got one line further to go. A little tiny bit of simplification. 4 times 1/18th is 2/9. And minus 5 times minus 1/9 is 5/9. So 2/9 x to the negative 18th minus 5/9 x to the minus 9 plus c. And if you want to be a little bit pedantic, we can take that minus off the 5 and we can put it into a plus right there. Those two minuses will cancel out into a plus. So our final answer, 2/9 x to the 18th plus 5/9 x to the minus 9 plus c. And if you want, we can take this bad boy and we can check everything out just by going, all right, let's take a derivative of our answer, 2/9 x to the 18th plus 5/9 x to the minus 9 plus c. Take a derivative. What'll I get? I'll get 2/9 times 18 x to the 17. Oops, let me make that a little bit cleaner. I'm writing at an angle there. 2/9 times 18 x to the 17 plus 5/9 times minus 9 x to the minus 10, and that plus c goes away. Now all we have to do is simplify a little bit. So 2/9 times 18, 2 over 9 times 2 times 9 is just 4 x to the 17th right there. Now, this minus 9 and that 9 will cancel out into just a minus 1, so minus 5 x to the minus 10. And hey, wouldn't you know it, that's what we got after we did our little tiny bit of simplification, converting that rational function into a more manageable just sum of powers of x with some multipliers out front. So hey, those two guys, same. These are the same. So we did it right. Kind of cool. You can always check your work. Neat.
Just do it! Don't let your dreams be dreams. Yesterday, you said tomorrow, so just Do it! Make your dreams come true! Just do it!
おめでとうおめでとうおめでとうおめでとう
おめでとう。
おめでとう
めでたいな。おめでとうさん。おめでとう。おめでとう。
おめでとう
おめでとう。